Thank you for joining me on the road to quantum reality. If you've watched the earlier videos, you will have seen how it is entirely possible to generate Schrodinger-like results for stationary structures from the application of the real-wave quantum mechanics procedures, and that such structures encapsulate spin rather than needing it to be in some way intrinsic. We got these rather beautiful structures when we did the sums for a simple harmonic oscillator potential in 2 dimensions. And we showed that one of their key features was phase alternation between adjacent FRs, and also showed how it was this feature which led to the isomorphism with the Schrodinger solutions. You might have noticed that in this slide there is a reference to the de Broglie fork, and I probably owe you an explanation of this. It is because, in my opinion, de Broglie got very close to real-wave quantum mechanics, but physics, again in my opinion, took a wrong turn at this point. So in this video and the next one, I want to justify this opinion. In this video, we take a quick look at de Broglie's work, and in the next video, we set out to show how real-wave quantum mechanics covers some of the same ground. We start with a quick look at de Broglie's role in the development of quantum mechanics and the way it is now somewhat glossed over in modern teaching, effectively being taught in Quantum Physics 101 as he postulated that if waves could have particle-like behaviour, then particles can have wave-like behaviour. And then he postulated that if so, they would obey the equation P equals hk. That is, the wavelength would be inversely proportional to the momentum. Schrodinger was able to use this relationship in developing his wave equation, and quantum mechanics never looked back from there. By the way, I'm not criticising Quantum Physics 101. There is a lot to cover in the subject, and since most of its practical applications stem from solving the Schrodinger equation, how this was arrived at is, relatively speaking, only of passing interest. But here's an interesting thought. How come we ended up with Schrodinger isomorphism for our stationary solutions without ever, at least knowingly, introducing P equals hk? We'll come back to that at another time. Anyway, de Broglie. I remember this picture from my childhood. It's a very deceptive picture. I've actually heard a tuition video telling students to remember that the electron is moving in and out towards the proton. De Broglie was the bridge from the old quantum theory of Bohr to the wave equations of Schrodinger, Klein-Gordon and Dirac, which followed. Before we get started in detail, I just want to make a quick note about nomenclature. I'm using the modern terminology of omega, k and h bar, rather than the frequency f, wavelength lambda and h used by de Broglie in his thesis. The relationships are given here for your reference. Okay, so back to de Broglie. Despite what Physics 101 says, de Broglie did not postulate P equals hk. What he did postulate is far deeper and more revealing for us. What he actually did was based on special relativity. It was a key input to his thinking, yet you'd hardly think so from a cursory examination of many modern physics textbooks. Another aside, within special relativity, the factor square root of 1 minus b squared upon c squared crops up all over the place. So rather than cover pages of maths with this factor, it is common to write gamma equals 1 upon the square root of 1 minus v squared upon c squared. Doubtless there are very good reasons for doing this, but with apologies to physicists, I'm going to avoid the inverse definition. Instead, I will just be using the empty square root sign to signify the square root of 1 minus v squared upon c squared. Now, all that is required is to remember that this square root symbol is always 1 or less. Then if you remember that clocks run slower and a clock can be thought of as a frequency, then the expression for that frequency must be omega equals omega naught times the root symbol, because the latter is less than 1. Likewise, distances get shorter and masses increase, so the expression must be m equals m naught divided by the root sign. De Broglie was interested in the two Einstein equations, E equals mc squared and E equals h bar omega. If you're mathematically minded, it seems very easy to take two equations, both of which are telling you something about an energy, and to equate them. But you can't just do that, because the energies are in fact related to quite different things. In the first equation, E equals mc squared, the energy relates to the mass, while in the second equation, E equals h bar omega, the energy is the energy of a photon, which is a massless object. There is no automatic ability to equate these two energies. But de Broglie did equate them, not because of simple mathematics, but because of a physical insight. He said, "One may imagine that to each portion of energy with proper mass m naught, one may associate a periodic phenomenon of frequency omega naught, such that m naught c squared equals h bar omega naught." In short, he was trying to allow these two energies to be the same by assuming a particle has a frequency. It has some clock-like characteristic. That is what is new and entirely original. But when he tried to pursue the consequences of this idea, he found a major difficulty. In the first equation, c is a relativistic invariant, which means that the speed of light is measured to be the same by all observers. In the second equation, E equals h bar omega, h bar is a unit of angular momentum, and this is also known to be relativistically invariant, also measured to be the same by all observers. So if these two energies are to be equated, and the constants of proportionality within the equations are both relativistically invariant, it follows that m naught and omega naught must behave in the same way relativistically. But we know from special relativity that the mass changes as m naught divided by the square root. So the frequency must change in exactly the same way. Omega equals omega naught divided by the square root. We now find ourselves with two equations for a frequency which look entirely different. It would have been very tempting to give up at this point. It is potentially very confusing, but one of these equations refers to what would happen to something oscillating within a moving particle, so let's call that omega p for particle, and the other is a frequency relating to how the mass must change, say omega m for mass. The first one is easy enough to understand. It is just like a clock. De Broglie decided to identify the second one as a frequency associated with a wave. But de Broglie's act of genius was to recognise that while the frequencies had to be different, they may, in fact, be referring to exactly the same thing. The particle has an oscillation frequency which must be in lockstep with the wave passing through it. It's not the frequencies which are the same, but the phases at the particle location. And he called this postulate the harmony of the phases. His postulate was a physical principle, not an equation. He did not postulate P equals hk. He derived this equation from his physical postulate, and it is this which is revealing for us. He called the wave which would meet this condition a matter wave, and he had everything he needed to calculate it. It was just a matter of mathematical manipulation without further physical input to derive the two relationships, his famous P equals h bar k, and the less well-known one relating the phase velocity and the particle velocity, Vp times Vm equals c squared. Because the maths is not required to appreciate the results, I have included it as an appendix to this video. As usual, these things are much easier to understand if they can be visualized, so let's do that now. In this simulation, we can see how the de Broglie relationships pan out in practice. We can set the speed of the particle, Vp, as a ratio of the speed of light in the top box. The de Broglie matter wave is plotted in red, and the particle location and phase are represented as the blue line starting at the origin and moving right at the velocity Vp. If we set the velocity to 0, there is no matter wave as such, because k is 0. There is no waviness. The two frequencies, omega p and omega w, are identical and have the value omega naught. Next, we increase the velocity a small amount, say to 0.01. Actually, this small amount corresponds to a very high velocity in human terms because the speed of light is so large. In fact, it is about 7 million miles per hour. Even so, this velocity is small enough that it doesn't perceptibly alter the frequencies. But the matter wave, that is, the phase wave, is now very obvious. We can see the particle is now in motion and see phase harmony in action. The blue line always corresponds to the amplitude of the wave. At v equals 0.1 of the speed of light, we begin to see a divergence between the frequencies, 6.31 for the wave and 6.25 for the particle. The wavelength is appreciably reduced. The wave is very much more wavy. At v upon c equals 0.5, the trend continues. Notice that the phase velocity of the wave has come down to twice the speed of light. Finally, at v upon c equals 0.9, the slowing of the particle clock is very obvious at 2.74, while the wave frequency has increased to 14.4. The phase velocity of the phase wave is down to 1.11, so there is not a huge difference between this and the particle velocity. These animations display the de Broglie phase harmony principle in action. Notice that we have merely represented the particle clock as an oscillator. The blue line is just moving up and down, and this is what de Broglie did. But we could equally have interpreted this phase as the phase angle of something rotating, so really analogous to the hands of a clock. Real wave quantum mechanics does this, which is the main reason we have started by looking at de Broglie. Because the product of the particle velocity and the phase velocity of the wave is c squared, and because the particle can never travel at faster than c, it follows that the matter wave is always superluminal. It is not a real wave. Nothing real moves faster than light. But it could be giving information about something which is real. Through real wave quantum mechanics, we will show that this is the case and come to understand what this information is. Anyway, the important takeaway is that de Broglie did not simply postulate that P equals hk. He derived it from relativistic principles and a much more fundamental postulate about wave and particle phase harmony. The postulate of phase harmony has rather got lost in the mythology of quantum mechanics, but it is this postulate which is going to carry through in a greatly enhanced manner to real wave quantum mechanics. Okay, now let's have a look at the mathematical derivation of P equals hk and Vp Vw equals c squared. We've already used and discussed these expressions, so this section of the video is really like an appendix for anyone who is interested. It's quite a nice derivation, and it does show the way that the relativity square root signs drop out. It might be of interest to those just starting to study quantum mechanics. We're going to use the existing equations for the two different frequencies, one for the particle and one for the wave. We will also be using Einstein's two equations for the energy, E equals h omega naught and E equals m naught c squared. De Broglie was able to equate these two energies. We should notice that there is only one value of omega naught, because when the particle is stationary, the frequency of the wave must match the frequency of the particle. So we can rearrange the equation to give omega naught equals m naught c squared over h bar. This frequency is known as the Compton frequency, and it plays an important role in real wave quantum mechanics and also in regular quantum mechanics. We'll keep these three equations on this page because we will need to refer to them during the derivation. The standard form of an equation for a wave moving towards the right is given as psi equals sine kx minus omega t, but we could equally well have written it as sine omega t minus kx. The difference between the two forms is just a phase factor of pi. Both of these refer to a right-bound wave. As an aside, if we wanted to refer to a left-bound wave, we need the expression within the brackets to be either both positive or both negative. I'm going to use the bottom form for this derivation. De Broglie's great principle is the harmony of the phases. The phase which we're referring to in this equation relates to the part within the brackets. We could call the phase phi w. The phase for the particle is simply the frequency of the particle as observed from the rest frame multiplied by the time as observed in the rest frame. So we can put phi p equals omega p t. Now, implementing the harmony of the phases principle, we can equate these two phases. The next step is to express all of the frequencies in terms of omega naught, and we can do this using the expressions on the left hand side. We note that the velocity of the particle is simply the distance x travelled in the rest frame divided by the time. We can rearrange this. The time is equal to x over Vp, where Vp is the velocity of the particle. Now we can substitute for t in the above equation, and we get this form. We would very much like to express kw in terms of omega naught. We can do this by recognising that kw is in fact omega w over vw, where v is the phase velocity of the wave. The phase velocity is the velocity at which the wave crests are moving. This expression is a general one for all waves. We can re-express the term for omega w in the third term using the expressions on the left. And now every term contains an omega w and an x, so these can be cancelled. Now rearrange the equation so that the term involving Vw is on the left hand side and multiply through by the square root. The square root squared is simply the original thing that was inside the square root brackets, which is 1 minus v squared upon c squared. So we substitute this in, and by opening out the brackets, the ones cancel to give. Now cancel 1 vp, and rearranging we get the required de Broglie expression. Now let's have a look at the derivation of the more famous equation P equals hk. We start by working on the expression Vp Vw equals c squared, which we just derived. We will also use the normal expression for the phase velocity of a wave, re-expressed in terms of the wave vector. Combining these equations, we get an expression for the wave vector k in terms of the wave frequency omega w and the velocity of the particle Vp. Now we can make use of the middle equation on the left hand side to substitute for omega w, and then we can substitute for the Compton frequency using the lower left equation which we have to give this expression for kw. Notice that the speed of light squared term cancels, giving this equation. And finally, note that m0 divided by the square root sign is in fact just the relativistic mass. So we can substitute this with just a simple m, and we get this equation. But the mass times the velocity is of course just the momentum, so we're done. We have P equals hk as required. Thank you for watching this video. Please like and subscribe, and don't forget to tell all your physicist friends.